Minasan, konnichiwa, Zamurai Engineer desu. In this video, let us go to the next module, module number 04, about failure of structures. So, failure of structures, our topic of discussion for today. This is your professor, again, Dr. EYPEI, ZANTUA. I am a civil engineer from Taguig City University. Let's start with the objective of the course. Principles of steel design provides us with fundamental concepts, principles, and theories on the structural analysis and design of steel elements in an structure. And we have 8 main topics. Currently, we are on the introductory portion of the course. And under this introduction, we have 5 subtopics. We are now on the failure modes of structure. What are the failure modes? Let us discuss. Again, discuss by reviewing the properties of steel, because steel is the main component. So therefore, any failure that will happen is with regards to its characteristic properties and its strength. Okay, steel is an alloy of iron with carbon composing about less than 2% and manganese less than 1%. It also contains small amounts of phosphorus, silicon, sulfur, and oxygen. What is carbon steel? So there are carbon steel, there are alloy steel. So if we say carbon steel, these chemical elements are controlled to provide consistent quality and grade of steel. So carbon steel, we have a controlled amount of carbon added to the iron. Carbon content greatly affects properties of steel. More carbon increases strength, hardness, and corrosion. Oh, we need somewhat more carbon within that given range. Given range 0 to or 0.1 to 2%. So that is the range. Okay. So as you increase the strength, also increases hardness and corrosion. This is that. And if more carbon decreases, what will happen? Going in the other direction, it will decrease malleability, ductility, okay, and weldability. So the amount of carbon does not affect the modulus of elasticity. So E. So because as you can see, the modulus of elasticity is another property of material. Okay. So and the amount of carbon does not affect that type of property. So again, take note, more carbon increases strength, hardness, corrosion resistance. In the same way, more carbon decreases malleability, ductility, and weldability. Okay. I will show you one specific issue in our country. We have a video about 4 or 5 years ago that became viral due to this, okay, with respect to these types of properties. Okay, and the next one, what is an alloy? Alloy is carbon steel. It is also carbon steel to which one or more chemical elements have been added to achieve certain physical or chemical properties. So it is a carbon steel plus something that is now alloy steel. Okay, so the most popular example is stainless steel, wherein 15 to 18% chromium and 7 to 8% nickel. So it's very small 7 to 8% is very precise. Okay, 15 to 18% very precise, even up to this day. Even up to this day, that is the industry standard. We cannot say 7. Okay, we cannot say 8. So that small window, 7 to 8, is already precise. No? Adding those type will produce a material that have very great corrosion resistant. Okay, as what we can experience with stainless steel. Another example is weathering steel. So stainless steel obviously prevents corrosion, but weathering steel, or what we call curtain steel, actually adds copper and phosphorus and create corrosion on the surface. It creates initial corrosion on the surface, but the corrosion on the surface will actually prevent further corrosion. Okay, so it creates steel that forms oxide. It will become a coating. The corrosion on the surface will become a coating that adheres to the base metal and prevents part. So it is stuck up there. Okay, unlike the normal corrosion of the steel, so the surface will corrode, and after some time it will become descale, no? So, or it will become uh, uh, easily separated from the main body of steel. So the surface which have iron oxide or rust will continuously get separated continuously, and then exposing a new surface which is again susceptible to corrosion. That is the normal thing. So the surface will become iron oxide, then will be detached from the surface, then another new surface is susceptible to corrosion, and then will corrode, and then so the cycle continues. That's why the steel after some time will fail due to what decreasing amount of material. Okay, so it will decrease the amount of material due to corrosion. Okay, however, curtain steel is not like that. It will corrode at once, but the corrosion will become coating because it will adhere to the surface of the steel. So that is what you can see on the picture on the left side of your monitor of your screen. So that is curtain steel. So it is corroded all throughout, but it is now preventing further corrosion. Okay. So in a more detailed manner, let us classify different types of steel, starting from point of view of what percent carbon. For example, if we have 0 to 0.2% carbon, we call that as wrought iron. Okay. If we have 0.2 to 2% carbon, we call that steel. Okay. 0.2 to 2. Okay. 0.2 to 2, that is steel. And 3 to 4% or less than 3 to 4%, that is cast iron. So meaning greater than 2% up to 4%, we call that cast iron. So it's very hard, but also brittle. Okay. So on the other hand, wrought iron is soft and malleable. Okay. So when we are talking about steel, we are 0.2 to 2% plus controlled amount of manganese, phosphorus, silicon, sulfur, and oxygen. So iron, carbon, MPSSO. Manganese, phosphorus, sulfur, silicon, and oxygen. So that is now our carbon steel. So what are the normal types of carbon steel? So mild steel, medium steel, hard steel, and spring steel. On the other hand, if we add combination of chromium, cobalt, copper, molybdenum, nickel, tungsten, and vanadium, to the carbon steel, we have what? An alloy steel. Okay? And alloy steel, we have two main types of alloy steel. We have stainless steel and weathering steel. So MPSSO, that is the elements added to steel, while if you add another set of elements like CCC, triple C, MNTV, and MNTV, triple C, 3C, MNTV, meaning chromium, cobalt, copper, molybdenum, nickel, tungsten, and vanadium. 3C, MNTV. Okay, so remember that MPSSO, 3C, MNTV. Right, so those are the elements that we need to be added into mixture of iron and carbon. So if you do that, you will have alloy steel, and there are two most common popular type of alloy steel. We have stainless and weathering steel or corten steel. So let us talk about the different types of carbon steel. So between 0.2 to 2%. We have mild steel, medium steel, hard steel, and spring steel. So remember, as we increase the amount of carbon, the result will gain strength, okay, and corrosion resistance. Okay, so how about mild steel? That is 0.2 to 0.25 mild steel. So it is very near to the property of wrought iron. So mild steel, wrought iron. So we have what? Medium steel, 0.25 to 0.45 carbon. Okay. Hard steel, 0.45 to 0.85% carbon. And lastly, spring steel, 0.85 to 1.85. So it's very specific. Okay. So let us continue. Now, let us relate those things and analyze what will happen. So because the material would fail because of stress, and one of the type of stress that builds up inside. So it is a type of stress that builds up inside the material, what we call residual stress, builds up inside the material. So stresses can be left behind in steel shapes after certain events. So it is inside the material because of forming it in that shape. Okay, so hot rolling due to differential cooling, because you put high temperature, and because of difference in temperature after cooling. Okay, so there is some likelihood that stresses will be retained inside the material. Okay, so that stress is what we call due to differential cooling. Also, the same way when you weld the material. So after welding, okay, the property was okay, but there's a residual stress inside or around the welded portion. Okay, so the stress is retained. Okay, so this residual stress is somewhat like like that. Okay, if you there is stress inside our joints. That's why our knuckles. If you press the knuckles, it will have a knocking sound. Okay, that's the sound. Okay, that's the sound because there is a residual stress retained on the joints. Okay, due to so many reasons. Okay, so many reasons. There are so many reasons. One of which is differential temperature. Differential temperature. In our in our culture, we call that in our dialect as pasma. Okay, okay, pasma. Okay, so pasma. Okay. Because of differential temperature, pasma. That's why you can you can uh, see somebody or be familiar with the way somebody treat those physical stresses by putting on warm, compress, or massage, or what uh, warming the body by putting on some bottle with hot hot bottle, hot glass, okay, at the back. That is to release the stress. That is to release the stress in conjunction with massage. Massage releases the stress. Okay, massage releases the stress. So similarly, material has those type, but you cannot massage steel. You cannot massage steel. How can you do it? We cannot massage steel in the way that we massage people, but we can massage it in principle. In principle. Principle meaning we have to make or do a process to the steel in order to release those stresses. But it's very hard to perform because there are several different stress direction. Okay, okay, direction. We don't know what is the real direction for that particular. So it's very hard. As we will see along the way. Cold forming, hot rolling. So cold due to plastic deformation because you are pressing the material. Okay. So 1 and 2 are due to temperature and cold forming due to plastic deformation because you are pressing it. Okay. And next, excessive deformation. If there's excessive deformation in some areas, in some spots, there are stresses retained. Okay, so those are what we call residual stresses. Okay, so these are the example of residual stresses due to forming. No, so either hot rolling or cold rolling. We can We can make a raw material steel to become like H, no, or W type, okay, W type, W type, W type, W type, and so W type 4 by 13, Okay, W type 4/2. Okay, next, W type 8/31. We will explain later on what do we mean by these names. Okay, W type 8/67, W 12/65, W 14/426. We will explain what do we mean by this name. These are W type. Okay, as an example. So, idealized residual stress in hot roll shape, meaning after hot rolling, we are able to get this desired form and shape. However, inside the material, we have what? Remain the residual stress. Okay. So here, for example, the there is a two example of W type shape. Okay. So in the first part here, the first part, we have H over B is less than 1.2. Okay. What do you mean by H? H is the height. H is from this point to this point, the extreme fiber. The extreme fiber from the top flange to the extreme fiber of the bottom flange. So from that point to this point, that is the H. So if you have that value, divide that value by B. What is B? The width of the flange. So H is height divided by width of the flange. If the result, if the quotient is less than 1.2, okay, less than 1.2, then we have this type of what? Stresses. We have these common stresses. These are the theoretical stresses, right? So we have what? What are the amount? Positive 0.5, negative 0.5 here. Negative 0.5 from the end of the flange going straight 0.5 at the center of the flange. Okay. And again, going down straight negative 0.5 on the other edge of the flange. Okay. What about vertical stress? Stress, this is look, this straight line is the neutral axis. So similarly, this line is the neutral axis. So we are what? Visualizing the amount of stress inside the material. Okay, we are visualizing. Okay, these are the stress inside the material. So, very small stress, but well, we have to take note of those because 0.5 also on, or even if very small would have an effect, no? Have a considerable effect if you ignore. Okay, so again 0.5 going that way, and that is positive stress. Okay, so we use what? We use negative stress here at the middle, and then positive stress at the another edge. Okay, so this are what actually stress on the web. This is the web. This is the web component. This is the stress on the web. So this is the stress on the flange. So it is a mirror image for the stress on the lower flange. Okay. So what about the next one? The next set. This is another W type. Another W type. Okay. Another W type. But now H divided by B is greater than 1.2. Take note of the what? The threshold. threshold is 1.2. So if you divide, H divided by B is greater than 1.2, and take note of the stress, negative 0.3 instead of negative 0.5. Then at the center, positive 0.3 instead of positive 0.5. Okay? So there is a limited residual stress if H divided by B is less than or greater than 1.2. So that is for flange, the upper portion, and again, that is a mirror image if you would like to know the residual stress on the lower flange. Take note, this is very specific. Upper flange, lower flange, and web. So what is now the residual stress on the web? This is the residual stress on the web. Okay, so positive 0.3, the top, going to the center, negative 0.3, then again positive 0.3. Take note of the sign also, positive, negative. So it looks like what? It looks like a roofing system. It looks like a roofing system. Then here it is what? Looks like an arrow pointing at the left direction. So it looks like an arrow pointing at the left direction. So going there, going to the left. Okay. So take note of that. So if H divided by B is greater than 1.2, 0.3 is the common value. Okay. And if it's less than 1.2, 0.5. Okay. So take note of that. Let's take note of that. For example, we have H shape, same, and we are given 5 different H shape, W type. So W type shape, so different sizes, very small, small, medium, large, very large. Okay, okay, and look at the flange pattern. So this is the flange. This is the flange. Okay. So compare this now to this. Okay. So this looks like what? This looks like H divided by B is less than 1.2. This looks like H divided by B is less than 1.2. But look at the, so it doesn't look like a roofing system with straight lines. So take note of the residual stress. Okay. There is more about, there's more residual stress on the edge of the flange. Okay. Not the same magnitude at the center. Same magnitude here, 0.5, 0.5, only opposite direction. Opposite direction means one is compression, the other one is tension. That is what we meant. No? And compression is, I think, compression is, we call it usually a negative. Okay, compression, we call it usually negative. I don't know. We will check later on how they call it here. So, but the important principle is that compression has a opposite direction with tension. So, meaning to say, due to hot rolling, there are stresses like this. Look at the web. Look at the web. And then look here, the web. Okay. So, okay. This is supposed to be like this. This is supposed to be like this. This is the flange stress. No? That is a flange stress pattern. Okay. Residual. So look at the stress. And this is better. This is better looking, but it is not a straight line. Okay. Okay. And lastly, this one, we have what? Take note, we have what here? So positive is tension, I am correct. So negative is compression. So when we say negative, that is compression. Here, this means negative 20. This means negative 20 compression. Okay, this is negative 0.5 compression. At the center is positive 0.5 tension. So at the center, there is 5. This is 5 KSI tension. 5. So if you take note, so this is about 5. Okay, about 5 KSI tension side. So this is about 20 KSI compression. Okay, so what about this one? So the same what? The same graduation, the same measuring stick. Okay, the same measuring stick. Put it here. So this is about what? 15 compression. So this is about negative 15 KSI, and this is about 12, right? Or positive 15. So this is about what? Okay, so more than 10. So this is about positive 15, negative 15. So this is more like it. This is the what? This is the graph that nearly looks like the ideal graph. This is the ideal graph without stress. Okay, so normal stress rather. We have stress because we have tension and compression. We have tension and compression, but here we have additional residual stress. We have additional residual. That's why it looks like this one. Okay. What about the next one? There is no tension on the this type. No? There is no tension. Everything is compression. So about 10. So this is about 10. So then decrease to 5 and then back to 10. How about this one? This is about 5. This is 5 tension, and then this is about 15. Okay, so this is about 12. This is about 5. Something like that. Okay. Now let's take a look at the web. Okay, take a look at the web. So these are the web pattern for residual stresses. Take note. The more stresses we get, those are the parts that could easily break down. Okay, that could easily fail. So just like we are talking about failure modes, we want to see which portion of the material would fail. Okay, so that is our intention here. Okay. Okay. So about on the web pattern. So web pattern, the same type, but look like what? This supposed to be what? Looks like inverted roof pattern, but look, the web. All what? All are tension here. All are tension here. Okay. So for the web, this is what? Positive is tension. So this is tension, this is compression. So compression on the center, tension on the outer web. While here, center is tension, compression of the edge of the flange. Okay, so compression and then tension is center. Here, compression is center. So here, what supposed to be what tension supposed to be tension on the outer web. Okay, this is tension, but everything is tension. Everything is under tension. Next type, we have what? Tension, then compression, almost in all. This means from this point, tension, then immediately compression, then tension on there. So that is what we mean by this. Okay. So what about this? Reverse. No? We have what? Compression, then tension, then compression. Okay. Next, supposed to be, we have tension. This is correct. Tension. This is the most what? Near to the our model. This is our model. So this is the nearest one to our model. So tension, compression, then tension. Meaning here, we are feeling the tension, then compression, then tension. Okay. So tension, compression, tension. Remember that because here, this is compression, compression here, tension, and compression. But when we are talking of web, we have what? Tension, compression, at the center, then tension. Okay. All, then the last example, all tension. We are feeling all the tension here from this point to that point. All tension. Varying magnitude. It looks like what? Parabola. Okay. So they looks like parabola rather than what? Straight lines. Okay. It looks like parabola. Okay, so recall this type of stresses when we are dealing with hot rolled chip. Okay. Next, what about welding effect on the residual stress? We have this. So welded portion, we have the welding on this cross section going there. So when we are doing that, we can feel compression, tension, and compression. So in this area, the material is feeling compressive stress. On that welded place, welded point, we have tension. Then go back to so in graphical form. So this cross section would feel here compression, then tension, then go back to compression, then zero. Okay. So this part, there is what? There is what? Neutral, no? There is a neutral stress here. Neutral stress meaning zero. So there's a neutral stress here. Some distance from the corner of the welded slat, no? Okay. So this is a slat. This is a slat for welding material. Okay. So that welding material is actually about here. So about the average here. Okay. So this corner is about this one, which is the middle or the average of this height of tension. Okay. It looks like what? It looks like a sine. No, cosine. Cosine wave. It looks like a cosine wave. Cosine wave, but what? Dump cosine. It is a dump cosine, which is symmetrical at the center of the well. Symmetrical center. So dump cosine function symmetrical. So now let's talk about degree of precision, because we will use computer, we will use apps, we will use, or you can use Excel, we can use computation, we can use calculator. So let's discuss the degree of precision. The accuracy of engineering data is less than 1/4%. Take note of this, 1/4% accuracy of engineering data. So making computation less than 1/4 is not worthwhile, because anyway the accuracy of the data is 1/4%. Okay. So what do you mean? 20.5 is okay, not 20.55, or worse, 20.55125. So this is the worst answer. This is not okay, but probably acceptable. This is our accepted, because why go further? Your result, your computation result. No need to go further on this level of computation, because anyway the accuracy of engineering data is less than 1/4%. Okay? Okay, less than 1/4%. So this is okay. This answer is okay. And not this one, or this is the worst answer. Okay? You might think this is the most precise or accurate answer. That is your opinion, because you are what? You are very much into mathematics. Engineering is not mathematics. We are using mathematics, but engineering is not mathematics. Okay? We want to use mathematics in our solution, in our methods, but we are not mathematics. No? Our courses is not mathematics. That's why this doesn't mean anything. Actually, it means worse. It is better to present it like this. Okay. Next, represent final solution values numerically to an accuracy of 3 significant digits. 3 significant digits is enough. If the number begins with 1, take note, then use 4 significant digits. If the number starts with 1. Otherwise, use 3 significant digits. So, for example, okay, this is 3 significant digits. This is 3 significant digits. This is 4 significant digits, because the number starts with 1. Okay? Because the number starts with 1. That's why we use 4 significant digits. We use again, this is 4 significant digits, because it starts with 1. We use 3. We use 3. This is 3 significant digits. This is 3 significant digits. Take note. We are using 3 significant digits here. This is 4 significant digits. Why? Because we start with 1. Okay. So there is one rule. Use 3 significant digits. Right? Why? Because the accuracy is 1/4%. Okay. Okay. So 3 significant digits. 1/100 is 1%. Okay. So that is still okay. But more than that, if you add another digit, you 1 over 100. 100 is 3 significant digits. So 1 over 100 is 1%. But 1 over 1,000, if you add another significant digit, you have 4 significant digits. That means 1,000. 1,000 is 4 significant digits. So 1 over 1,000, that is 0.1. So that is less than 1/4%. Okay? So take note of these 3 significant digits and use 4 if you start with 1. Intermediate values are computed to 5 significant digits to avoid rounding errors. Okay? So, intermediate values, meaning to say, you are not yet going to present the final answer. Before computing the final answer, you have previous formula and compute it, and then you have the intermediate result. After getting that intermediate result, you are going to use that in order to apply the formula with that value in order to find the final answer. So if you are dealing with intermediate values, use 5 significant digits, okay? Just to avoid rounding errors, okay? Use 5. So what are the important significant digits? 3 is our general rule. If the starting point is 5, I is 1. If 1 is the starting number, use 4. And if we are doing our intermediate operation, use 5. Okay? So if this is what? Intermediate operation, 5. So up to 1. So 20.551. Use up to this portion. If that is intermediate. So even intermediate, this doesn't make any sense. This doesn't make any sense. So in intermediate, this is acceptable. We have an intermediate operation. This is acceptable. But in final answer, this is the acceptable result. Okay. Take note of these things. Okay. Design concept and rationale. So let us move to this because there are this is another way where we get failure on our structure. 1, residual stress. 2, we have imprecise computation. Okay, and there are a lot of example, real life stories, real life narrative. Okay, that happened in the past that due to those computation mistakes, errors, they have what failure. Okay. Another, let us first discuss the concept of design and its rationale. Okay, so we have again what the diagram in a prediction of the structural analysis. We have what? There are 5. Okay, so we have load on this axis. On the y-axis, we have load. We have deformation of this, meaning we have what? Stress strain diagram. So this is a stress strain diagram. Okay, load and deformation. So we have what? We can use strength load or we can use service load. Okay. So what do we mean by strength load and what do we mean by service load? Service load is the type of load that is used in operation. Okay. Strength load is usually used in our design process. Okay. It is related to the material capability. Okay. So number 1, we have what? We have first order elastic analysis. So if this is a stress strain diagram, we have first order analysis is what? Straight line, elastic. Straight line is elastic. So the proportional what? The proportional point. Okay. Take note of pure. We have the pure. Okay. Proportional point, elastic limit, the yields point, then ultimate and rupture. So pure. So here, first order analysis. So we have a straight line, meaning we have what? Elastic. This is elastic. So this is an elastic part. So number one. Number two, first order plastic analysis. We are now going plastic. Okay. So this is elastic. So this is the first order elastic. Elastic meaning from this point, it is not a straight line anymore, and therefore we already know that this portion elastic, this portion is plastic. Okay, plastic meaning the material will not go back to its original form and shape. Okay, so it will continue to be deformed. It will continue to be deformed. Okay, elastic meaning if you release the pressure, you release the stress, it will go back to original form and shape, size. Okay, so that's the difference between. So they are both first order. So first order meaning this is the ideal. First order, that is what we mean first order. The ideal effect of the elastic. This is the ideal effect, first order plastic. Okay. Number three, second order elastic analysis. Okay. Still, this is elastic, but this is now second order. So, from the straight line of first order, we are going here. And it is in the middle of first order elastic and first order plastic. So, it is somewhat in the middle. Okay. So, it is a beautiful, smooth curve. Okay. And this smooth curve is actually having what? Number four, elastic stability analysis as it's what? It's maximum. Okay. So it will what? Be deformed like this, never touching the number four, but will go deforming like this. Okay. So number four is the next one, elastic stability analysis. Okay. So this is the stable value. Okay. Stability with respect to elastic. Elastic stability analysis. And number five, advanced analysis. So this is more realistic in real life. So advanced analysis, this is the real model. So advanced analysis. So even though we are able to make the first order analysis, it is somewhat useful. If you do the first order plastic, it's somewhat useful. Second order analysis is somewhat useful. Elastic stability analysis is somewhat rough. Okay, not very precise, but that is a boundary. Okay, I think that is maximum boundary condition. So realistic one, the most realistic one. This is still not equal to the real situation, but this is the most realistic model that we call advanced analysis. Okay, so we have the number five. Okay, so member behavior, meaning the steel members. Okay, so again we have what? The load and the formation diagram, how this member behaves. So look, linear, number 1. Number 2 is what? Material non-linearity. So this is number 2. Okay? Number 3, geometric non-linearity. Okay? So number 1 is linear. This is what? First order elastic analysis. Number 2, material non-linearity. So it's look like first order plastic analysis. Okay? So that is first order plastic analysis. But that is when we are talking of the behavior or characteristic of the material. That is material non-linearity. Okay? Number 3, geometric non-linearity, or the number 3 here, which is second order elastic analysis. So it looks like this. Okay, so number 3. And number 4, buckling. So that is our buckling part. So elastic stability analysis. So that is the maximum. Over that is actually the boundary wherein the material will buckle. Okay, so that's why we don't need to reach that. We don't need to reach that. This is the type of buckling. If we are having what? A column or post. So as we compress it further, the column will buckle like this. Okay, looks like this. Okay. So number 5, we have what? Advanced analysis. And when we are talking material, that is material and geometric non-linearity. This one. So material and geometric non-linearity. And number 6, in addition, we have fully plastic. Take note, the stability, elastic stability, and fully plastic model here. Okay. So fully plastic model. And number 7 is local buckling. So local buckling is shape similar with number 5, but is smaller. And number 8, if we have a brittle material, so immediately it will break here. So number 8, brittle fracture. So knowing those things, we talk of design concept and rationale. Okay. So let us now take a look on strength, stability, and stiffness. Okay. So